Compiler construction 16. So last time what we did is well, in the last two classes we added functions, top level functions. And so what we're going to do today is we're going to add closures or lexically scoped functions. So we're going to be updating our language from R5 to R4. So we have R4 and we're going to R5. I just wrote a 5 twice. All right, R5. So what we're going to do is we're going to take our E language and we're going to add in a new form, which is we're going to add in lambda, a variable, then there's going to be a sequence of variables with their type, and then we're going to have the return type, and then we're going to have the expression. Okay, so this right here is a recursively bound name. These right here are the arguments, and those are the argument types. This right here is the return type, and this over here is the body. So let's look at a little function that we could do. Naturally, we're going to use our favorite friend, factorial. So we could write the following program where we have an application where we are applying lambda fac, and it takes as an argument n, which is an S64, and it returns an S64. And the body of this function says if n is equal to 0, then return 1, otherwise multiply n by factorial of n minus 1. Close the multiply, close the if, close the fac, and do 5. And I just realized that actually we haven't told you how to do multiply. I mean, of course, you could just go do it by using the multiply expression rather than the the multiply instruction rather than the addition one. But let's not make that assumption that you've done that, and instead we'll change this. Let's have it not be the factorial function. Let's call it be the fad function. And what the fad function does is it has an addition there. So it's like an addition version of factorial. So you give it 5, and it does 5 plus 4 plus 3 plus 1 plus 2 plus 1. Okay. So this right here is the example function. Because this is recursive, that means that we can now write arbitrary recursive functions. We can, of course, encode for loops, right? Because all a for loop is just something like this, where we just have some variable there iterating over, running the body every time. Okay. Now, when you extend your interpreter, you'll want to represent these closures in some way. And actually, you know what? I should make a note about what do I mean by closures. Of course, like again, this class doesn't really make sense unless you've done the OPL class. So let's just do a really concrete example. So suppose we had let x equal 5 inside of let f equal lambda, where there's no return thing, and then we have a y, which is an S64, and we return an S64, and what we do is we do a plus of y and x, close the lambda, and then we have this inside of let x equal 6, inside of f applied to 6. We close the application, close the first let, second let, third let. So this program evaluates to 11, not 12. And the reason that it evaluates to 11 is that this x right here is the same as that x. And so the 6 goes in. Sorry, I wrote 6. Yeah, but I meant to write x right here. To write x. So we're calling f on x. So an x flows in, its value at least flows into y, and then we have a 6 there, and then this x refers to that 5, and so we get 6 plus 5, which is 11, not 12. That's what I mean by closures. Okay, So, let's talk about how to change the type checker. 16.3. So the rule is really quite straightforward. We have delta and gamma, and we are checking a lambda. So we have a lambda with some function f, and we have some argument 0 with domain type 0, and we have a whole bunch of those. And then we have the return type, which is the range, and then we have the body E. And so the result of this is a function that takes in the domain types and then returns the range. And then this is true if, when we take delta and we extend gamma with a mapping that goes from A0 to domain 0, and then we also extend it with a mapping that goes from F to this function right here. So let's just say that this right here is called the function type that goes to the function type. If that proves that E has type range. Okay, so that's what we do for the type checker. And notice that because we require the programmer to specifically write down what the types of all these things are and the range, that's why we can synthesize the type of f. We don't have to do any guessing or inference or anything like that. Okay, next thing. How do we change the random code generator? So obviously, you could have lots of different ways of changing the random code generator, where you could make it so that, sometimes you generate a function that has 10 arguments or something like that. My advice is that you know that your code already generates lets all over the place. So what you should do is just make it so that half of the time, rather than generating let x equal xe in B. Now when I say half of the time, what I mean is that you have some code that already generates this let sometimes. So you just make so that half of the time, rather than doing that, it instead what you get is a new lambda with an x, the b on the inside, and then an xe. What this is going to do is it's going to sprinkle all over your program a whole bunch of lambdas. And some of these are going to be, close over things, some of them aren't, and you're not really going to be able to detect when that's going to happen. Now you may notice that we're not testing situations when you have multiple bindings. So maybe what you do is you generalize to, a small number, like a random number between, like 0 and 4 or something like that. A small number of random arguments, so that rather than generating a single thing, you'll generate something like lambda of x0, x1, x2, x3, and then the body, and then you'll have xe0, xe1, xe2, and xe3. So essentially what you could do is you could make it so that sometimes your code that introduces a new variable will instead introduce it as a lambda rather than as a let. And when it does that, it randomly picks a small number of variables to actually add. This is an easy way to do it. Now you may say to yourself, okay, well, what about the recursive thing? Here's where there's not really a good way to randomly generate this. Because here's the thing. Remember how we had this stress about we need to randomly generate programs that type check? Well, if we allow our random program generator to randomly generate recursive programs, we'd have to have it randomly generate recursive programs that actually finish running. And that's kind of hard to do. If you really want to, what you could do is you could basically make it so that it randomly generates for loops sometimes, where you meticulously code in, like, what does a for loop look like. You can do something like that. Okay, what do we need to do for the optimizer? Basically, the main thing that you want to do is right now you already have a rule in your optimizer that says when you apply some function expression to some arguments, what you do is you could turn this into a let where you explicitly say, here argument 0, sorry, like x0 is argument 0, and you do that for, x1 and argument 1, and so on for all of the arguments, and then you have the body. And you do this when fe is known. Now, what it means to be known is where known is some top-level function that you're calling. Okay? What you could just do is you can make it so that another thing that counts as being known is when it's a lambda, when it's a concrete lambda with, x, whatever, body. So you could say that when that's known, you do it. But now here's kind of the annoying thing, is that, what if you use the recursive name? So what you'd have to do is you'd have to not only bind the arguments, but you have to bind the recursive name to this function again, just in case it gets called again. So you can totally do this. I would recommend that being the extent of it, because doing more analysis to try to figure out when lambdas flow to other places is more complicated, and in fact that's exactly what the next unit is all about. So yeah. Okay. What next? You're gonna have to modify, uniqueify, reveal functions, all of those things. But what's gonna happen actually, that's pretty cool, is that we're gonna be able to implement this extension of our language by simply making an additional pass that takes an R5 program, and turns it into an R4 program. Meaning that since it's an R4 program, we don't actually have to change any other part of our compiler at all. Everything else will just work, which is really cool. That process is called closure conversion. And what I want to do is, I want to give a little example of how it's going to work. And then what we'll do next time is we'll actually work through like the actual definition of how it works. I think that's what we'll do. So here's what we'll do. Like, imagine we have in our program, let's go back to that example that I wrote before. Let's go back to this program. I'm gonna write down manually what this thing is going to turn into with closure conversion. All right. And we'll put it right here. All right. Okay, so it'll turn into the following. Notice that we've got this lambda right here. So that lambda is going to turn into a data structure. Because what is a closure? A closure is a data structure that has a pointer to some code and then a pointer to the free variables. So essentially what we're going to do is we're going to get define function 27, where function 27 takes in the argument, what's it called? The argument clo, where the closure is a vector of S64s, and then it also takes in y, where y is an S64, and then it's going to return an S64, right? And then what does the body of the function look like? Let's, by the way, imagine that I didn't write an underscore here, or imagine I wrote r. Then the body of this function is going to look like this. It's going to say let r equal f27 in let x equal vector ref, which I'm going to write as vr, clo 0, close that parenthesis, in plus yx, close this let, close that let, close the define. Then what's the rest of the program look like? The rest of the program looks like let x equals 5 in let f equal a vector where this vector has f27, and then after f27 there is a vector with a x in it, and then we close that vector, and we have this inside of let x equals 6 inside of, oh, now I just really want to fit it all in. Right. I think we can just barely make it. Inside of, what we're going to do is we're going to pull out from this vector f. We're going to pull out from that vector, oh sorry, this is supposed to be a VR. Okay, we're going to do VR f 0, that gets us the function reference, and then we're going to call it with VR f1, and then we're also going to give it the variable x. And then that closes the application. Then we close the let, close the let, close the let. Okay, so this right here is what we turn our program into. Now notice that there are a few key ideas. This lambda right here, its body was lifted up to the top of the program and turned into this define right here. And this define takes an additional argument at the front, the closure, and that additional argument has inside of it as a vector all of the free variables. Then what the body of the function does is it uses the name for the recursive function. It binds the free variable to an element of the closure, and then has the existing, the previous body. And now this lambda right here, the time then we tried to create it, it gets turned into calling a function f and calling it with, that function, it actually constructs a vector, which is the function itself, and then the vector argument. That is the closure that stores the free variables. And now what the call does is we take the call and we pull off the function, we pull out the closure, and then we provide the rest of the arguments. So this process is called closure conversion. All right. Now what we'll talk about next time is how to actually implement this, and what are the sort of nitty-gritty annoying pieces that show up when you actually try to do it. So we'll talk about that next.